Alright, so let me give a bit of a preamble on what is going to happen today. So, last time we finished our first discussion of the universal algebra, and we're kind of just going to do a reset here. We're going to discuss it again from the beginning, but this time in a different way, from a different text. Hopefully we should still see a lot of interesting things happening despite the fundamental material itself being the same, potentially. So universal algebra, and this is our alternate study. We're going to let G be a Lie algebra over a commutative ring K. Now, this alternate definition, a universal algebra of G is a map eta from G to here. We're writing the universal algebra as UG, where UG is an associative algebra with a unit such that, first off, epsilon is a homomorphism, so it is linear over a ring K, and it acts on brackets by sending them to that, as you'd expect. And secondly, it is initial, which means if A is an associative algebra with unit, and we have a morphism from G into A, exists a unique homomorphism phi from UG to A such that you map from G, you have this canonical map from G to UG. I guess we don't know it's canonical yet, technically, because we're restarting our study. But essentially, from this embedding, which is going to be every homomorphism from G to A is going to some A is going to filter, going to factor through this UG. This diagram is going to be commutative. And they give an alternate notation for this, which is that the homomorphism, the set of Lie homomorphisms from G to the Lie algebra associated with A is isomorphic to the associative Lie homomorphism, the set of associative Lie homomorphisms from the universal algebra of G into A. So essentially, we can, as I said, we can write any homomorphism from G to the Lie algebra of A as a homomorphism from the associative Lie homomorphism from the universal algebra of G into A. And from category theory, that we have that UG is initial, and so if it exists, it is going to be unique up to isomorphism. So we do need to prove that UG exists, but we have uniqueness and everything else by category theory. So we're going to recall the tensor algebra of G being T of G, which is the direct sum from 0 to infinity of the tensor of n elements of G, which is sum of the tensor product of n copies of G. And this is actually universal for bilinear functions. So we have, for any associative algebra, A with unit we have that the set of the module homomorphisms from G into A is isomorphic, is equal to directly the associative Lie algebra homomorphisms of the tensor algebra, so associative module of the tensor algebra of G into A. As always, we're going to let I in TG be the two-sided ideal of TG generated by, you should know the idea here, x tensor y minus y tensor x minus their bracket. They right here the negative of this, but it's the same. And we take UG to be TG over I. And theorem 2, we have a theorem here. We're going to let epsilon the map epsilon from G to the universal algebra of G, and this is going to be the map from G into T1G, because keep in mind T1G is just a tensor of one element of G, so a product of one element is just that element, so that's a very obvious map. And this T1G is inside of TG, so there's an easy map there. And then we quotient out the ideals, which exists entirely in T. It has components in T2, so that's not really going to change anything either for this map. And under this epsilon are UG defined as the quotient of TG and I with this map epsilon is the universal algebra of G. As you'd expect, this is a pretty clean way of defining it, I will say. Of G. So we're going to let alpha be a Lie homomorphism of G into an associative algebra A. Since A is k-linear over our base ring K, it extends uniquely to a map, a homomorphism from the tensor algebra of G into A. And we saw this before. It just I believe it just splits across the tensor product in the way that you would hope. And now the image of elements in I under this map is going to be 0. We've seen before. Because, yeah, we've seen it before. So then it defines, so essentially that means we can divide it by I, which gives us a map from our UG is TG over I into alpha. And we see this, because of how it's based on alpha, it is going to be the equivalent of alpha for TG into A instead of G into A. And yeah. Okay, what a remark here. Let E be a G module G is a Lie group. So that is a K module with a bilinear product essentially G scaling on E such that it cooperates with the Lie bracket in G. That is, the bracket of two elements in G acting on E is just x, ye minus yxe. This is, of course, for x, y in G and E in E. Then the map G to the endomorphisms of E which defines the module structure of E is a Lie homomorphism. Just keep in mind what this is doing is sending each, if you have for each x in G, we have x is getting the sent to the function that sends E in E to x times E. It's, as before, it's currying this product that we have up there. And so hence, it extends to an algebra homomorphism from the universal algebra to the endomorphisms of E. So E becomes a universal G left module. This gives an isomorphism of the category of G modules to the category of UG left modules. Alright. So let's look at what they call functorial properties, which is certainly a name for a section. Oh, and we're going to do that on another page. First off, if G is the limit of G alpha, then the universal of G is the limit of the universal of each G alpha. If G is the direct product of G1 and G2, so G1 and G2 will commute, then the universal algebra of G is the tensor product of the individual universal algebras. Three, K prime, extend K, and G prime be the extension of G by K prime. Then the extension, the universal algebra of the extension is the extension of the universal algebra. And we saw a proof for these before, We'll go over the proof of number 2 again, but yeah. So we're going to pick homomorphisms eta epsilon I from each gi to its universal algebra. And we're going to also have another homomorphism of f from G to the universal algebra of G1 tensor UG2. We're going to find that as f of x being epsilon of x1 tensor 1 plus 1 tensor epsilon of x2. With x1 and x2 being the decomposition of x into g1 and g2. F is a Lie algebra. How do we know F is a Lie algebra homomorphism? That's because G1 commutes with G2. Because keep in mind, this is the direct product is a semi-direct product where that map from G2 to the derivations of G1 is the 0 map. So we're left with no interaction between the two. And so it induces an associative algebra homomorphism C from the universal algebra of G to UG1 tensor UG2, and this is just the universalizing of F. And so we also have homomorphisms from each gi into G being the natural injection, which then gets sent into the universal algebra of G. Which, and these induce homomorphisms phi from UGI into UG through the same process. Once again, by this commutativity between G1 and G2, we have that phi1 of x1, phi2 of x2, and these two elements are going to commute. So essentially the images of G1 and G2 under phi1 and phi2 are going to commute because it's a homomorphism. So now we're going to take phi be a map from UG1 and UG2 into UG, given by, for its image on a tensor, we just split it up and use these individual component tensors. And we see from our condition before that the composition of phi with C in either order are the identity maps for each relevant domain. Like I said, this is going to go much faster this second round through, because we're already going to go ahead to the symmetric algebra of a module. Probably shouldn't abbreviate titles. Once again, G is a K module, and it's going to be commutative. GBK module as a commutative Lie algebra. So essentially the bracket is just always 0, as we've seen. Then the universal algebra is going to be the same as the symmetric algebra. With the symmetric algebra of G being the universal algebra of G. And keep in mind, so the way we generate this symmetric algebra for an arbitrary Lie algebra is we strip off the bracket, put on a bracket which is just 0, and then you construct the universal algebra as before. And keep in mind, the generators of ideal reduce down to saying that the tensor product is going to be commutative over the symmetric algebra, and yeah. So we can define SG, they say here, as the largest commutative quotient of TG. That is the sum of from 0 to infinity of SNG with SNG being the set of n tensors of G over the ideal I is generated by x minus sigma x for sigma in the symmetric group of G elements acting on X by permuting its components in the way you'd expect. So yeah. So let's look at a case. Let G be a free K module with a basis of elements EI for I in our indexing set. And we're going to let epsilon be a map from G to the polynomial algebra of these xi. Some indexing set. This is once again the polynomial ring with indeterminants matching up to our basis. There's homomorphism with, of course, epsilon of xi mapped to the respective indeterminate. Then epsilon with this polynomial ring is universal. It's a universal algebra. Then epsilon with this polynomial ring satisfies the universal property of the universal algebra. That is for all k linear maps from G into A, into some A, which distributes over the product fx, fy equals fy, fx, commutes, and there exists map f star from k of xi, I in I, to the algebra, to whatever A is, such that f star of epsilon is f. As f star of some polynomial is the polynomial of f of component of basis ei for p in the polynomial ring that we are working with. And so thus we can identify the symmetric algebra of G with the polynomial algebra of K of indeterminates. And if we have a total ordering ordered, we have a basis as before of the product of ascending basis elements, which we saw plenty of that before. Okay. Next topic is the filtration of the universal algebra of G. So let G be a Lie algebra over K so we define a filtration of the universal algebra of G as follows. We're going to let UNG inside of UG be the submodule generated by product of epsilon dxi for xi in G. So essentially it's generated by the product. Keep in mind epsilon is the injection of G into UG. So it's essentially the products of at most n or less, that's n or less elements of G inside of UG. So we then have that the 0th submodule UG is K. With that U1 G is K with the image of G in UG. With I less than J implying that U of UI of G is contained within UJ of G. We define GRUG here, I like to call it, the graded version of the universal algebra of G as the sum. We're going to index it with n, not I, of the grades of UG, with each grade being the quotient of the nth copy of G over the n minus 1th copy of UG. You know what I mean? Then the map from the from U sub P of G and U sub Q of G into U sub P and Q of G, which is just their product. Defines through the quotient a bilinear map from the pth grade of the universal algebra of G and the qth grade of the universal algebra of G into their sum. This gives the graded algebra of U of G. Let me just rewrite that whole thing. This gives that what we're calling the graded algebra of the universal algebra of G. Sorry, probably not going to edit that out. As a proper graded algebra, as you would hope by the name. And it is associative, and it has a unit. Alrighty. So, well, let's give ourselves a quick proposition here. This algebra, the graded of the universal of G, is generated by the image of G under epsilon, which is the map from G into the universal algebra of G. And let's look at the proof. We're going to let alpha be an element GR in the nth grade of the universal algebra of G. And we want to split it up into components inside of the image of G. And we're going to let alpha hat in UNG be a representative of alpha. That is, if you quotient alpha by UN minus 1 of G, you quote alpha hat of UN of G by UN minus 1 of G, you're left with alpha. So we have that alpha hat is equal to the sum of m mu less than n of lambda mu times the product. We go by the indexing from 1 to m mu of the images of some elements xi mu. So we can write alpha as being elements of grade n lambda mu, and then the product up to m mu of the images of these xi mu under the quotient map. Pretty good. And let's go one more proposition here, one more theorem, I guess. This is just a simple one to state that the graded algebra of U of G is commutative. And we saw that it's generated by epsilon G. So all we need to show, we need only that each of the images of any two x and y in G, their images in the U of G, and then their image of that in the grade commute. And that's going to take place inside of the second grade of the universal algebra of G. As epsilon is a Lie algebra homomorphism, then we get that epsilon of x, epsilon of y, minus epsilon of y, epsilon of x, is just epsilon of the bracket. which is contained within U1 of G, which means that which is equivalent to saying that Ex epsilon y is congruent to epsilon y epsilon x mod of the first grade of U sub 1 of G, which is equivalent to saying that epsilon x epsilon y, the product of their quotients, is epsilon y epsilon x. Pretty easy. And it follows from this that the canonical mapping from G into the graded universal algebra of G extends to a homomorphism which they use this weird I for, from the symmetric algebra of G to the graded universal algebra. And since graded universal algebra of G is generated by epsilon of G, the image of G in the universal algebra, we have that I is surjective. And that, I believe, is not quite half of our rediscussion of this stuff, of the universal algebra. It's going to go in a different direction, but like, it's good to go over again like this new notation and some alternate proofs just for completion's sake, you know?